proving the optimality of the Grover's algorithm, and to do this we need to find some vector phi for which this double inequality is true. And we already proved that for the right part of inequality holds for any unitary vector phi, and it's time to prove the left part. You remember our decomposition of some very effective, the most effective algorithm provided by somebody, by some algorithm designer. And the operators U, omega here are queries to an oracle, and these operators U1, U2, etc. up to UT are the operators provided by the algorithm designer. Now we are going to introduce this vector phi t, which is defined like this. We get this most effective algorithm, and instead of all the oracle queries, we put the identity operators. And this trimit algorithm we apply to the initial state of the system, vector psi 0, and after t iterations we get this vector phi t. Now we are going to introduce some auxiliary values. The first one is this E of omega nt, and the E stands for error, because our trimit algorithm is obviously erroneous. It doesn't call the oracle. Instead of an oracle, it calls the identity operator. So we are going to estimate how much deviation from the correct path we get on each step. So let us recall what is this U omega operator. It is identity minus 2 omega and minus this identity, and everything is applied to psi t. Okay, now these identities go away, and what we get just two scalar products of omega and psi t. Now we are going to define this function f of t, which is the deviation of the correct vector and the vector provided by the trimit algorithm on the step t. Let's rewrite it for the previous step. It's ut, u omega to psi t minus 1 minus ut phi t minus 1. And since the operator ut is unitary, we can remove it from under the norm. And I'm going to add and subtract this value under the norm. Let's see what it gives us. So we have u omega psi t minus 1 minus psi t minus 1 plus psi t minus 1 minus phi t minus 1. And this is our error here, and this is f of t minus 1. So we're using the triangle inequality to get this. Okay, and for the step t, we can use this recursive definition that we get and this estimation for an error. So we have these two from here, and the sum from t equal to 1 up to t big is modulus omega psi t minus 1. Okay, we get this, and for the inequality we have to put squares here, because in the middle part of inequality there is a square. So we get this, and finally it looks like this. Well, now you remember we proved this lem in the previous episode, in the previous lecture. And since we proved it once, we can use it as many times as we want. So we use it. And this appears to be less or equal. And for t, and the sum here of is omega psi t minus 1 squared. And we don't need a brace here. Just let me think if I put everything correct. I think I did. And you remember in the middle part of inequality we have this sum over all vectors of the space, so we sum it over all omegas, and we get this expression here. This one we just obtained in the previous slide. And I'm going to change the places of these sums here. So it is equal to for t, sum over t, then sum over all omega. All this dot product squared. And you can see that this sum here is actually the norm of this vector psi t minus 1, which is actually 1. So we have t runs here from 1 to t big. We have t big once, and it is 4t squared. And we just proved the left side of our double inequality for the vector phi t.